Good afternoon, ladies and gentlemen. A cordial welcome to the International Space Science Institute's Game Changer Seminar Series. Today we have the 8th edition of the cycle, Viewing Earth from Space, the Changing Environment and Climate of Our Planet. My name is Michael Rast. I'm the Earth Sciences Director at ECE in Bern. I'm particularly happy today to welcome Clement Albergel. Clement is working at the European Space Agency's Climate Office in Harwell in the UK, where he develops climate applications which are related to terrestrial surfaces and associated modeling schemes. Before he came to ESA, he was working as a scientist at the European Centre for Medium Range Weather Forecast, the ECMWF in the UK. And before that, he was a scientist at the French Meteorological Service, the Météo France, where he was working on land surface analysis schemes. His activities at ESA basically three-pronged. Besides working on the climate program, about which we will hear today, he's also supporting the International Global Development Assistant, which is one of ESA's projects, in EU Africa, which is a research and development facility which are implemented under Directorate of Earth Observation in ESA. Now, Clement will today report on ESA's Climate Change Initiative in support of terrestrial carbon science. And before I hand over to Clement, I would kindly ask the participants on the call to submit their questions, please, through the chat, so that at the end of Clement's presentation, I can moderate a little bit the questions and I will read them out so that Clement can answer them. Clement, a cordial welcome. Many thanks that at a relatively short notice you were prepared to give this presentation today, which we all are looking forward to. And with that, I would hand over to you. The floor is yours.
Thank you very much, Michael. Thank you for the introduction. So indeed, my name is Clement Albergel, and I work at the European Space Agency Climate Office. And my main line of activity, as mentioned by Michael, focuses on ESA's climate program, the Climate Change Initiative, that we implement at the Climate Office under the Directorate of Earth Observation Program. And this talk is for me the opportunity to give you an overview of the Climate Change Initiative, its rationale, and some of the data sets we produce, as well as how they can be used. I will mostly focus on our projects related to terrestrial variables, because that's what I do. And I will show you how some of them can be used in support of carbon science. But first, some background. Climate change is arguably the greatest environmental challenge facing us in the 21st century. The consequences of a warming climate are far-reaching. The early heat wave we just had in Western Europe is just another sign, a glimpse of our future climate. And with worsening impacts predicted for the natural environment and society for generations to come, climate change is high on political, strategic, and economic agendas worldwide. The Intergovernmental Panel of Climate Change, IPCC, has released last year in August the key findings of the Working Group 1 contribution to the Fixed Assessment Report on the physical science basis of climate change. The report provides new estimates of the chances of crossing the global warming level of 1.5 degrees in the next decades, and find that unless there are immediate, rapid, and large-scale reductions in greenhouse gas emissions, limiting warming to close to 1.5 degrees or even 2 degrees will be beyond reach. And this has been further confirmed earlier this year by the IPCC Working Group 2 on Impact, Adaptation, and Vulnerability. Now, IPCC is here to provide scientific assessments of climate change. Combating climate change requires a global effort. The United Nations Framework Convention on Climate Change, an environmental treaty, is leading the international efforts to combat climate change and limit global warming to well below 2 degrees Celsius above pre-industrial levels, as set out in the Paris Agreement for Climate. UNFCCC is the body responsible for driving global climate action. And to achieve this objective and to make decisions on climate change mitigation and adaptation, the UNFCCC requires a systematic observation of the climate system. And that is precisely why the role of space agencies, of the European Space Agency, is crucial to climate and to climate action. Satellite Earth observation has the capabilities to contribute to achieve the main goals of the Paris Agreement for climate in many ways. That can be through further effective policy making and or policy implementation monitoring. For example, as part of the Paris Agreement, all parties agreed to a global stocktake every 5 years, starting in 2003, to assess the collective progress towards achieving the purpose of the agreement and to inform of further individual action to be taken by parties. Parties have to report their greenhouse gas inventory every year, their emissions and removal. And they are also required to submit their anthropogenic emission reduction goals as part of the national determined contributions, the NDCs, every 5 years. So we can feel that there is an urgent need to monitor the progress. We need to have access to regular update of greenhouse gas budget at country scale, and Earth observations can help. In their reporting, national emission inventory agencies are currently using bottom-up approaches combining activity statistics with emission factors. Very little use is made of satellite Earth observations, only by a handful of countries. And that is probably also because we do not have yet Earth observation, satellite Earth observation data that quantifies greenhouse gas fluxes directly. Rather, we have observations of variables or proxies that can be transformed into fluxes using models. In this context, we can use Earth observation in different ways. It can be through top-down atmospheric inversion, combining atmospheric greenhouse gas measurement from in-situ monitoring networks or satellites with atmospheric transport model, the idea being to backtrack concentration to its source. Or we can use bottom-up approaches based on process-based dynamic global vegetation models, DGVM, or bookkeeping models for natural and human fluxes that we can constrain with Earth observation, satellite Earth observation, such as land cover and land cover change. Earth observation can also be used to improve the emission factors used by national agencies. The capabilities of Earth observation satellites in support of climate information needs reflects the unique abilities and benefits. They have wide area observation capability, are non-intrusive, provide uniformity, rapid measurements, and continuity. And that is precisely why the role of the European Space Agency is crucial to climate and to climate actions. ESA has been dedicated to observing Earth from space ever since the launch of its first weather satellite back in 1977. And this slide illustrates the Earth observation missions we have developed over time in the context of the three main lines of activities of the Earth Observation Program Directorate: Earth Science, Copernicus, and Meteorology. With the launch of a range of different types of satellites over the last 40 years, we are better placed to understand the complexities of our planet, particularly with respect to global change. Today's satellites are used to forecast the weather, answer important Earth science questions, provide essential information to improve agricultural practices, maritime safety, help when disaster strikes, and all manner of everyday application. The need for information from satellites is growing at an ever-increasing rate. And with ESA as world leader in Earth observation, the agency remains dedicated to developing cutting-edge spacebound technology to further understand the planet, improve daily lives, and support effect policymaking for a more sustainable future. This slide is just to focus on the importance of the Copernicus program. Copernicus is, as you know, a project run by the European Union and the European Space Agency that builds and manages a fleet of Earth-observing satellites called Sentinel. Several missions have been launched already, providing data about changes occurring to the ocean, land, and atmosphere of our planet. Today, all land masses are observed every 5 days at 10 meters spatial resolution with Sentinel-2, and every 12 days at 20 meters with Sentinel-1. And this has never happened before. And those data is freely and openly available to anybody in the world. 250 terabytes of freely available satellite data are distributed every day. And we have long-term continuity well beyond 2030. Coming back to climate, our role at the ESA Climate Office is to provide a central point in coordinating all Earth observation work conducted by ESA relating to climate and climate change. Our primary activity is to manage ESA's climate program, currently the Climate Change Initiative, CCI, defining and overseeing all the CCI program work, checking standards and promoting quality, consistency and collaboration across the different CCI projects and other bodies. In particular, we work with the European Union Copernicus Climate Change Services, C3S, in relation to climate services, the working group of climate, that is a body of major space agencies responsible for responding to the UNFCCC, as well as the GCOS, the Global Climate Observing System, on the monitoring of climate from space.
Sorry to interrupt. Can you adjust your microphone a little upwards in front of your mouth, because the voice is sometimes going up and down.
Of course, of course.
Perhaps you put your camera a bit more in the center so that we can see your face when you look at it. Thank you very much.
Okay, sorry for that. I hope that's better now. So we are based in EXAT, ESA's home in the UK, on the Harwell Science Campus that is 15 miles south of Oxford in this very building. We are a team of 12, including application scientists like me, information architect, communication and knowledge exchange manager, a Future Earth research coordinator, an ESA research fellow, and a YGT. So for climate, what do we want to observe? As I said earlier, the UNFCCC requires systematic observations of the climate system. And they have delegated to the GCOS, the Global Climate Observing System, a public consultation to define a list of variables that represent best the climate system and its variability. And these are indicators of climate change known as essential climate variable, ECVs. An ECV is a variable that is critical for characterizing the climate system. They need to be observed or derived on a global scale using proven and scientifically understood methods. Generating, archiving, and disseminating them should be affordable, and they need to be observed according to the GCOS climate monitoring principle for consistency, traceable calibration, and for climate-relevant changes to be resolved. A bit more than 50 ECVs have been defined. Most of them can benefit from satellite Earth observation, and some of them can even entirely rely on satellite Earth observation. These ECVs support not only the climate information needs of the UNFCCC and IPCC, but also the wider climate community. So it is in response to UNFCCC requirement for systematic monitoring of the climate system that ESA launched its climate program in 2010. The Climate Change Initiative, CCI, is a coordinated research and development program amongst ESA's member states that generate robust, long-term, global satellite-derived datasets for key indicators of climate change. You would have understood I'm talking about the essential climate variable. And the CCI does this by harnessing, by putting together ESA Earth observation archives generated over the last 40 years and combining them with data from third-party and current missions. And that includes, of course, the Copernicus Sentinel missions. Under CCI, we currently have 24 dedicated ECV project teams developing 22 ECVs. And as you can see on this slide, each of these projects addresses specific variables in the oceanic, terrestrial, and atmospheric domains. And we also have horizontal cross ECVs activities, such as a sea-level budget closure project and the RECAP 2 project on regional carbon budget, as well as a dedicated climate modeling user group and a research fellowship program. When it comes to terrestrial carbon, we can then highlight most of the terrestrial projects we have, as well as the one on greenhouse gas in the atmosphere. But for sake of time, I will only illustrate a few of them during this presentation. Now, as you can imagine, we do not directly measure those variables from space. It is by sampling the electromagnetic spectrum at multiple wavelengths that satellite can build a more complete picture of Earth's complex climate system. Last year, we have prepared a short video to explain how satellites observe the Earth, and I would like to show it to you.
Satellites observe the Earth using a range of wavelengths on the electromagnetic spectrum. from short wavelength ultraviolet to long wavelength microwaves. Different wavelengths allow us to probe different aspects of Earth's land, atmosphere, and ocean. Light from the sun, shining at over 5,400 degrees Celsius, peaks in the visible part of the spectrum. Earth reflects sunlight, but also emits its own radiation at longer wavelengths. With a much lower average surface temperature of 15 degrees Celsius, Earth's radiation peaks in the infrared part of the spectrum. Many satellites use the reflected visible and the emitted thermal wavelengths to probe the planet's surface. The atmosphere scatters light at shorter wavelengths, sometimes making it hard to see the surface. We can often get a clearer view in the infrared. Growing vegetation strongly reflects near-infrared light. Surface temperature controls emissions in the thermal infrared. Satellites are also used to probe the atmosphere. Atmospheric gases absorb light at characteristic wavelengths. Sensors are tuned to the unique absorption patterns of different gases such as ozone, carbon dioxide, and water vapor. At longer wavelengths, water vapor blocks most of the signal from the surface, but we can still gather some information about the upper atmosphere. The atmosphere starts to clear again at microwave wavelengths. Microwaves emitted from Earth's surface tell us about soil moisture, ocean salinity, snow and ice. While some satellites tune into these emissions, others emit their own microwaves in the form of radar beams. Radar altimeters precisely measure the height of the ocean, glaciers and ice sheets. Scatterometers measure ocean roughness and wind speed. Synthetic aperture radars can take detailed images through clouds and at night, allowing us to continuously monitor vegetation, water bodies and ice flow. By sampling the electromagnetic spectrum at multiple wavelengths, we can build a more complete picture of Earth's complex climate system. With 23 climate variables and 40 years of satellite observations, ESA's Climate Change Initiative is tuning in to Earth's climate.
Right, so I didn't see the chat going mad, so I assume that it did work, and I can now start describing some of the ECVs we have. And as you can imagine, as you can see, this slide starts with a description of the fire CCI projects. Satellites permit to monitor different fire characteristics, areas that are dry and prone to wildfire outbreak, actively flaming and smoldering fires, burn areas, as well as smoke and trace gas emissions. And these Sentinel-2 images give you a nice illustration of some of those processes. Several satellites are currently available for fire monitoring with different capabilities in terms of spatial resolution, sensitivity, spectral band, times and frequencies of overpasses. Satellite can measure, as we have seen, electromagnetic radiation, the light reflected, and the heat emitted from our planet. And we can use different types of instruments, such as visible and infrared detectors. The visible ones can detect smoke plumes from fires, as well as burn scars on the land. And the thermal infrared one can detect actual hotspots and active fires. We identify from space areas on the ground that are distinctly hotter than the surrounding and flag them as active fires. And the difference in temperature between the areas that are actively burning with respect to neighbor areas allows the identification and mapping of active fires. Just to illustrate this, here you have two print screens from the Sentinel hub. On the left-hand side, you have a Sentinel-2 image, true color, for the 14th of August. This is in Spain, and you can see some smoke going across. And on the right-hand side, that's the same scene, same satellite, 5 days later, and you can see a contrast on the ground, a scar left by a fire. If you change the band and look at false color, you can see that this contrast is stronger at the latest date on the right-hand side of the slide. Looking at the shortwave infrared, the contrast is even stronger. And on the first image, the first date on the left hand side of the slide, you can see the active fire. So if you put the notion of risk monitoring and risk assessment aside, if we focus on fire in the context of the Paris Agreement for Climate, it is also because vegetation on land disturbed by wildfire has the potential to release significant greenhouse gas and particulate matter into the atmosphere. It is estimated that about 25 to 35% of greenhouse gas result from biomass burning, and therefore they are considered an important factor in climate change. The Fire CCI project, led by Emilio Chubieco in Spain at the University of Alcalá, focuses on the key variable burn area, using a hybrid approach combining surface reflectance and thermal anomaly. It has different products at global scale, derived from AVHRR, MODIS, Sentinel-3, but not only. It has recently focused on high resolution at regional scale using Sentinel-2 information at 20 meters spatial resolution to develop a small fire database covering sub-Saharan Africa for the year 2016 and 2019. And the results were really impressive. This slide illustrates the small fire dataset. And as you can see here, for a plot over Africa, over in Austral Africa, the 20 by 20 meters footprint of Sentinel-2 at the bottom right-hand side of the slide made it possible to detect way more fire compared to the 500 or 250 meters spatial resolution of global product previously used that you have on the top two figures. Over Africa, and for 2016, 90% more small fires were detected with the Sentinel-2 product than with the lower resolution MODIS product, and they contribute to nearly half of the total burn area detected. So corresponding fire carbon emission from African fires are clearly higher than previously thought. This is a substantial increase. Small fire are a critical driver of burn area in sub-Saharan Africa, and including the detected small fires in emissions estimates raises the contribution of biomass burning to global greenhouse gases and aerosol. So this is another example for another part of Africa in the western parts, and for the year 2019, when you can see that the finer resolution product here in the middle allows detecting much smaller burn area patches compared to the medium resolution sensor. And to convince you further of the importance of high resolutions when it comes to burn area, on this figure, you have the evolution of the total yearly burn area for different global moderate resolution products, the different lines. And on the top right, you have two dots in red and in black, representing the burn area derived from Sentinel data only for sub-Saharan Africa. And it is also very impressive to see the global data set based on Sentinel-3 synergy, a combination of the two sensors, OLCI and SLSTR, called Fire CCI S310. Here, this diamond, this green diamond here, presenting high value compared, for example, to the MODIS-based product that is here in blue. As I said earlier, we use a hybrid approach to detect burn area using both thermal anomalies information, hotspots, and reflectance value. The new Sentinel-3 derived dataset uses VIRS hotspots that has a spatial resolution of 375 meters instead of the MODIS hotspot used in the MODIS product, blue line, with its 1 kilometer spatial resolution. And this has definitely a major role. The Sentinel-3 base dataset also use shortwave infrared band instead of near infrared, and there were also some improvement done to the algorithm. So not only the Sentinel-3 based product detect 28% more burn area than the MODIS based one, but it also has a better accuracy. It is an improvement in the capacity to detect burn area from medium resolution sensors. Let's now talk about land cover. By comparing recent Sentinel data with historical records, we can map, for example, the overall changes in local rainforest coverage. Here you have two images from the same area in Brazil 40 years apart. One is from Landsat 5 and the other from Sentinel-2. And you can see how the landscape has changed. Earth observation data, such as this one and other data sets from the Sentinels and the Earth Explorers, are a key tool in helping to address climate change and in taking actions to preserve biodiversity. It is crucial to be able to go from a satellite image, such as this one, to a proper mapping of land cover and land cover change. Accurate estimates of land use and land cover change are crucial to support the global stocktake process I've mentioned in the introduction of my talk. The role of land for storing carbon and its future potential for offsetting carbon emissions is an area of active research. Modeling the interaction between vegetation, climate, and greenhouse gases can be supported by datasets such as those from the moderate and high resolution CCI land cover project to quantify change consistently across countries. The moderate resolution land cover project has a unique series of annual consistent land cover maps at 300 meter spatial resolution spanning from 1992 to 2020. And they are developing consistent annual plant functional types maps, PFTs, over the same period that will be analysis ready for climate modeling. Such a data set will likely become a very popular climate data record for the climate modeling community. The high resolution land cover is developing for now static maps for 3 areas in Sahel, the Amazon, and Siberia at 10 meter spatial resolution, along with long-term record of regional maps at 30 meter in the sub-region and every 5 years, and information about changes every year. And I will focus a bit longer on this data set. Each of these 3 zones has been identified as they correspond to a specific need from the scientific community. Over the Amazon, it is to study the impact of deforestation, fires, agricultural expansion on water and carbon cycles changes. In Siberia, it is to better understand the impacts of climate change on northern displacement of the forest, shrubs, grassland transition zone, the fate of permafrost carbon, and finally over the Sahel, we want to look at the impact of climate change on drought, flood events, and on the West African and Indian monsoon dynamics, as well as to develop mitigation studies, for example, the Great Green Wall, monitoring the Great Green Wall. On this illustration, you can see a map from the high resolution land cover, this right panel here over the Amazon, that is produced by fusing a Sentinel-2 image here in the middle panel, also combined with Sentinel-1 image at 10 meter spatial resolution. And the moderate resolution land cover is also shown here for sake of comparison. And as you can see, new details show tributaries to the main river and urban area classes that are otherwise omitted. Here you have 2 further examples of the details revealed at high resolution with respect to moderate resolution compared, for example, to an S3 image for natural areas. And you can see that you have way more detail on the coastline when you compare to this image when using the high resolution product. So ESA also has a project called World Cover that was a technical challenge to see if it were possible to produce for 1 year at 10 meter spatial resolution this time, a map of land cover, a global map of land cover. And the resulting map for 2020 has almost a 75% accuracy. And we are currently developing another map for 2021 with the objective of having a better overall accuracy of 77%. So here you have some example between the different products. On the top left, here you have the CCI medium resolution, a map from the CCI medium resolution product, high resolution here on the right, and below you have ESA world cover relying only on Sentinel-1 data and an S3 image. And you can see that the CCI high resolution product is the one that corresponds best to this image. So this is another example. So in a natural environment with the same kind of result, the CCI high resolution land cover, if you have just a visual check, better represents this image. And this is another map where you can see the different tributaries to the main river and the agricultural parcel that you don't see at medium resolution and you don't see with the ESA world cover product. Now, this is the first land cover map within the historical zone the project has over the Amazon, and it is centered, I believe, on Paraguay. for the year 1990. Apart from the southeastern part of the domain that is dominated by grassland, most of the domain is covered by trees. Moving by 5 years period, here in 1995, then 2000, you can see artificial structure are appearing, and you can see that grassland and cropland are step by step dominating the green, the forested areas. So if you, here we are in 2005, then 2010, trees are replaced by grassland and cropland. And here we are in 2015 and then 2019. So here you can see how the land use has changed over this domain from 1995 to 2019. And this is a final example to illustrate deforestation through the year from 1990 to 2019, as seen by the high-resolution land cover map. We provide this type of map every 5 years, but also the changes every year. The land cover change map, as seen here, for example, on the right left-hand side of the slide, as well as the probability of change, as you can see here on the right-hand side of the slide. We provide the first class and what will be the second class, as well as the associated posterior probability for the first class and the second class. So I think that's all I wanted to say about land cover. Now LST, land surface temperature. Land surface temperature is an important variable within the Earth's climate system. It describes processes such as the exchange of energy and water between the land surface and the atmosphere, and it influences the rate and timing of plant growth. It is integral to a radiative energy budget of the surface, and it provides the best approximation to the thermodynamic temperature that drives the surface energy. Accurately understanding LST at the global and regional level helps to evaluate land surface atmosphere exchange processes in models, and when combined with other physical properties such as vegetation and soil moisture, it provides a valuable metric of surface states. It is also useful to constrain estimates of terrestrial carbon uptake through data assimilation in Earth system model. The LST-CCI project aims to provide an accurate view of temperature across land surfaces globally over the past 20 to 25 years for climate applications by developing techniques to merge archive data from a variety of satellites into a combined long-term satellite data record. And although satellite-derived temperature analysis is well established, the new data sets provide the first climate record of LST, merging both infrared and microwave sensors at a global scale. The LST climate data record that has recently been released is the most up-to-date observation of such variable, and they can be used to gain a more comprehensive understanding of environmental change. Spanning the last 25 years, yes, the records show a stable increase in land surface temperature of 0.2 degrees per decade, although there is a considerable regional variability within this. And the data sets are accompanied by an objective assessment of their accuracy and have been fully validated for consistency and stability over time to ensure they are suitable for climate trend analysis. We have data that started in the 90s, and we have a continuity, for example, with the Sentinel mission. Here, just for sake of illustration, you have two maps of land surface temperature for two heat waves that had happened this year. A couple of months ago in India, with the land surface temperature higher than 55 degrees, and more recently in Western Europe, where we have reached 45 degrees of land surface temperature. The Paris Agreement requires parties to make progress on adaptation measures. So unlike mitigation, tracking adaptation is an emerging topic with targets and indicators that are generally lacking. We are really developing this field. So although not surprising due to the requirement of a range of locally specific information. So Earth observation has a potential to provide information to track adaptation progress. And here you have an example where Earth observation data can track progress to tackle the urban heat island effect. As you know, urban areas experience warmer temperature than their surrounding areas, and they are said to experience more severe and frequent heat waves as the impact of global warming progress. Incorporating green space or blue space, such as ponds in urban area, can reduce local temperature. And researchers from the University of Leicester proposed tracking adaptation effectiveness and progress of urban greening on thermal discomfort using LST information. The idea is to go from a measurement to an index we can track. So they measure the degree of urban greening and the resulting across city changes in thermal discomfort during future heat waves. On the left on side, you have a high resolution land surface temperature observation. In the middle, you have a derived urban heat index. And on the right, you have the thermal discomfort index. Surface temperature is combined with information such as humidity, giving a measure of the perceived temperature by humans. So there is a clear need for co-development of adaptation indicators, such as this one, in concert with stakeholders. Moving from LST to above ground biomass, GCOS considers above ground biomass an ECV due to its function as both a source of atmospheric CO2 when forest is lost under land use change or by degradation, and as a sink for CO2 due to forest growth. Information on forest biomass can also play a much wider role in understanding and predicting climate. For example, in model initialization and testing, estimation of carbon turnover, inferring the forest disturbance regime, and data assimilation in carbon cycle and climate models. Tracking biomass change over time is a useful contributor to the Paris Agreement global stocktake in the context of the NDCs, aiming at a better understanding of sub-decadal and decadal variability of the carbon cycle, for a more robust and transparent reporting in the UNFCCC, for the overall reliance of natural sinks for climate mitigation, and finally, it also contributes to a better understanding of carbon climate feedbacks, hotspots, and tipping point, as well as ecosystem collapse. New maps providing a global view of above ground biomass distribution and spatial density over 3 separate years have recently been generated, and they have been derived from a combination of data depending on the years from the Copernicus Sentinel 1 mission, NVSAT's ESA instrument, and JAXA ALOS 1 and ALOS 2, along with additional information from Earth observation sources. Now, the team also would like to address temporal consistency, and a possibility could be by integrating additional lower spatial resolution data streams, such as vegetation opacity, VOD, derived from ESA's SMOS satellite. And investigating such data set permitted to recently highlight that forest degradation has become the largest process driving carbon loss in the Brazilian Amazon. And the authors of this study have estimated that the Brazilian Amazon experienced a cumulative gross loss of carbon that is higher than the gross gain, resulting in a net loss of about 0.67 petagram carbon of above ground biomass over the last decade. Moving now to the call process. I'm aware of time, so I try to be a bit faster on the different ECV I present. I'm jumping now to permafrost, and the objective of this CCI project is to develop and deliver permafrost maps as ECV products primarily derived from satellite measurements. The required associated parameters by GCOS for the permafrost ECVs are the depth of the active layers and the permafrost temperatures. Rock glacier kinematics have been proposed as a new parameter and are also addressed in the permafrost CCI. Permafrost cannot be directly observed from space. So the team has identified algorithms which can provide these parameters, ingesting a set of global satellite data product in a permafrost model scheme that computes the ground thermal regime. So permafrost CCI strongly relies on the data product from recent, ongoing, and future ESA project. And there is a new 21-year record of permafrost describing the annual changes to the northern hemisphere permafrost soils from 1997 to 2020 at about 1 kilometer spatial resolution. And this is the longest satellite permafrost record currently available as far as I'm aware of. So using this data set, a very interesting study has recently been published where authors have tracked the loss of permafrost using satellite data. The active layer, the soil that sows and refreezes seasonally, deepened by an average of 2.5 centimeters across the northern hemisphere during 2007-2016 compared with the previous decades. And for about 5% of the area, the active layer has deepened by more than 30 centimeters. Permafrost is fracturing and disappearing. The deepening active layer not only destabilizes the landscape, but also makes more carbon available to microbes in the soil, producing carbon dioxide and methane. As I said earlier, under CCI and later under the future climate program of ESA, we develop ECVs by combining Earth observation archives with data from both third-party and current missions. And the CCI Soil Moisture project is a very good example. It produces annually algorithmically updated global climate data record of soil moisture spanning over more than 40 years, ingesting data set derived from the sensor listed on this slide. It develops 3 separate soil moisture products derived from active, passive, and a combination of both sensors. And to date, it has publicly released 13 datasets, each updated with any available new sensors and extended time series when applicable. Data are available at a 1/4 degree spatial resolution. And one of the coming challenges will be to develop ways to downscale the existing data so we can have higher spatial resolution, global, long-term soil moisture data. And we have kicked off the new phase of this project this morning. In May 2022, so very recently, we officially released the ESA CCI Soil Moisture version 7.1 to the public, and this saw several significant changes as compared to earlier versions. For sake of time, I will not develop them, but as for all our datasets, you are more than welcome to visit all our projects' webpage. This version of the soil moisture is our best soil moisture product so far. On the left-hand side, for example, you can see the fractional coverage from 2007 onward that is almost 1 during non-frozen condition. We have data every day. And on the right, on the top part of the slide, you have correlation for different versions of the ESA CCI soil moisture data compared to in situ and reanalysis from ECMWF. And the idea is that in time, with the release of new version, we always increase the correlation. So the soil moisture CCI product has contributed to hundreds of hydrological and climatological studies worldwide, as well as the annual Bulletin of American Meteorological Society State of the Climate Report for more than a decade now. And the latest one has been published last year in 2021 and focused on the year 2020. And with the next State of the Climate for 2021, that will probably be published end of August, if it is a similar timing as last year. So this illustration here is based on last year version number 6 of the soil moisture dataset. And here you have a global map of the average soil moisture anomalies for 2020 expressed in cubic meter per cubic meter, with respect to the 1991-2010 base period. For sake of time, I will not go to the details and jump to the next slide, where I will illustrate a different type of project we have, cross-ECV project. So, as I said earlier at the beginning of my presentation, adequate methods for estimating greenhouse gas inventories are crucial for accurate and consistent reporting of progress towards national determined contribution. And this is in the context of the Paris Agreement for Climate. And to that end, we can combine multiple ECVs together with modeling through cross-ECVs projects. The ESA CCI Recap 2 is one of them, and its objective are to, firstly, to evaluate the feasibility of producing updated estimates of greenhouse gas balance at country level, constrained by Earth observation data using an ensemble of top-down atmospheric inversion and bottom-up land surface models, but also to improve their consistencies against official estimates reported by countries to the UNFCCC. They are also working directly with national inventory agencies so they can provide greenhouse gas information that matches user need. During the last phase of the project that has ended earlier this year, the team has designed and implemented a comprehensive framework to process the result of atmospheric inversion in order to make them suitable for evaluating the estimates of anthropogenic emission and removal of greenhouse gas made by UNFCCC national inventories, what countries are reporting to UNFCCC. And this work represented a major achievement from a technical point of view, combining a large number of heterogeneous data sets from various providers, but also from a scientific point of view, where they had to reconcile, if you want, the process agnostic inversions they were developing with the process-oriented inventories, despite different definition of the greenhouse gas variable. So on this figure, you have the CO2 fluxes for land sinks and fossil emissions. If you look at the box plot, you have the inversion for different time period. In red, you have the fossil fuel, and in green, you have the land sink. And on the x-axis, you have the major emitters they have considered. Now, the little black horizontal lines represent the CO2, net CO2 fluxes for the inversion, and the circle, green or red circles, represent the mean of the UNFCCC national greenhouse gas inventories, what countries are reporting to the UNFCCC. If you focus on the green box plot, you can see that there is a striking consistency between the mean for each period of national greenhouse gas inventory, land carbon sinks, and inversions for all major emitters. If you focus here, for example, to the 27 member states of the EU and the United Kingdom, you can see that for the fossil emissions, the trend is the same between the mean of the inversion and the UNFCCC inventory. So, of course, there are many assumptions, many hypotheses behind this type of figure, but it really paves the way for countries and the global community to improve checks and consistency of national inventories to more accurately reflect global emission. And in the new phase of this project, building on previous experience and in coordination with the Global Carbon Project, the new phase of RECAP 2A for attribution, will enable the scientific community to make a significant step forward in the attribution of the global land carbon sink to land use change, fire and harvest disturbance and recovery, as well as climate effect using ECV data from the Climate Change Initiative, but not only, and also on the attribution of the global methane budget to natural wetlands, for example, open water, and anthropogenic sources. I think a last example I wanted to showcase is this one. Our data set can be combined, for example, to study land-atmosphere-ocean interaction. And this can lead to very interesting findings. You will probably remember seeing on the news the devastating 2019-2020 fire season in Australia, and particularly southeastern of Australia, where the fires burned an estimated 74,000 square kilometers of mostly eucalyptus forest. That is roughly 2.5 times the area of Belgium. And a paper that has been published last year in Nature and based on global inventory data sets of wildfire emissions using satellite fire data and modeled quantities of standing biomass suggested that the fires released on average 275 million tons of carbon dioxide between November 2019 and January 2020. However, a new analysis indicates that this figure was a gross underestimate. Using data from the Tropomi instrument on board of the Copernicus Sentinel 5P satellite, a research team were able to obtain a more accurate of the estimate of the emission, and then concluded that the bushfires had actually released 715 million tons in just 3 months. So that's quite a difference. In a companion paper, also published in Nature, a research team suggested that the aerosols generated by the record Australian bushfire season were actually sucked up by a gigantic phytoplankton bloom thousands of kilometers away in the Pacific Southern Ocean. Vast plumes of smoke, which are rich in nutrients, were swept away over the ocean. And within days, this aerosol had infused the waters with iron, nourishing phytoplankton, which then absorbed carbon dioxide equivalent to as much as 95% of the emissions from the fire. Looking to the future, 6 Sentinel expansion missions are now foreseen to address EU policy and gaps in Copernicus user needs, and to expand the current capabilities of the Copernicus space component. And these missions are a reaction to the most pressing question for which we need reliable information from a policy research and economy side. For sake of time, I will not go into the detail and will directly jump to what could be the last slide of this presentation, just a slide reflecting on the CCI facts and the figure. We have managed to gather a community of more than 400 scientists within ESA member state in Europe for more than 130 institutions. We are developing 24 ECVs, doing research and development. 15 of them has already been transferred to an operational climate service, C3S. We have our science leads, our scientific team have published more than 1,000 peer-reviewed papers. They contribute to the latest IPCC assessment report. All our data are freely available. I invite you to look at this website, and we have more than 600 terabytes of data, more than 200 data sets, and 9 million files. I think that was the last slide of my talk. Thank you very much for your attention.
Thanks a million, Clement, for this really excellent and comprehensive overview of ESA's Climate Change Initiative and the ECVs that you are observing therein. We're a little bit pressed for time, so I'll start with the first question that I got in the chat, which is from Steven Spangler. And it goes back to this land surface temperature example. Measurements from land surface temperature from passive microwave measurements require knowledge of the emissivity of the ground, i.e. how good a black body is. This emissivity must depend on the properties of the soil, which in turn depend on climate change. And this dependence of the emissivity on climate change well enough understood to permit unambiguous results on land surface temperature.
That's a very good point. And we know that we really have to better understand the impact of our changing climate on the variable we are trying to monitor. So LST is not one of my projects, but I trust that they do that correctly. What is more difficult to do looking at LST is to look at projection, because we don't know to which level climate change will affect the interaction between those processes.
Okay, then I have a question myself, and you have shown really fantastic examples where you're using Copernicus Sentinels, but also ESA's Explorer missions, as well as some missions from NASA, MODIS, for instance. My question is, with the oncoming panoply of constellations and small satellites such as Planet, are you already, or are your plans also to extend the use of satellite data to those small satellite constellations? Are they of any use for the 25 ECVs that you are observing?
Yes, definitely. And I think that we need to consider this, what ESA calls often the new space. And we need to look not only at what has been done in the past, but also what is available now, and a different panoply of measurements that can be satellite, new microsatellite, CubeSat, but also drones and in situ measurement. And for example, a very high resolution images are very important for evaluating, for validating the work we are doing with fire. Yeah. So we use this type of information. We also use, so we call that third-party mission, as you will know, and we have different agreement with commercial entities, so we can benefit from those information. Of course, this is a research and development activities. When it needs to be transferred to an operational climate service, we have to understand what is this boundary between commercial activities and public activities. But all this new space is really useful, and we are also triggering new studies to be able in the coming future to use the future development of ESA or other space agencies. So yes, a big yes.
Okay, I just have a question here from Tilman Spohn, our EC Executive Director, who asks, your plot of the source and sinks of CO2 showed that China has dramatically increased their carbon release, but also to some extent their sink. While for the US and EU, the sink stayed constant, can you explain how China increased their CO2 sink?
Or we will need to look better into that, but definitely it can be through adaptation and mitigation measure. We also have to understand, as I said, that there are many hypotheses, many assumptions behind this figure. We do not account, for example, through all what is the lateral exchange of carbon, or we just put some big assumption, and this needs to be better defined. For example, all the lateral transport through river, for example, but also through exchange of goods and yields. So it will be difficult for me to give you like that a big answer, but I'm happy to develop that further offline and to share with you the paper we've prepared on that.
You showed some example which made it very, very clear that the current and older generation of 20 to 30 meter resolution optical sensors are pretty much fringe in order to support your quantitative assessments within the among the ECVs.
Yes.
Where do you see the trend of spatial resolution and optical sensors go, Clement?
With the improved spatial resolution, for example, yeah. I think that it is very important that we continue to develop our global activities, and we will be limited with the spatial resolution that we have. But moving forward, we also need to develop climate data record that matches user need, and maybe we can have better regional focus. And I think land surface temperature is quite important. With the data we have now, it is difficult to look at application over urban areas where we need a much better spatial resolution. And we will have this kind of information, for example, with the coming LSTM. And so we need to be ready to be able to ingest this type of data and develop, as I've tried to illustrate at some point, indicator of climate mitigation over urban area. And this new type of data will definitely help.
And we'll probably need kind of 10 meters for that. Yeah, okay.
Definitely.
Yeah.
Sorry, go ahead.
I have a final question before we go, and that you showed this fantastic adaptation example with the urban heat islands, because we've heard from various experts more and more the focus goes on adaptation. Are there other examples in the CCI activities, contracts, and projects that you have that show such measurable adaptation, just as this example of the urban heat islands did?
I mean, this one is a very good example, and it's really something we would like to develop in the next climate program of ESA. So we are really at the beginning, and we need to but to engage better with local stakeholders to derive this kind of new generation of indicator.
Yeah. Okay. Thank you very much. We know, Clement, that you kindly made yourself available at short notice for this talk, but you have a time constraint. You have to escape in 2 minutes. I do get a lot of compliments and thank yous through the chat at the moment for an excellent and very, very interesting talk. Clement,
thank you.
Also, on behalf of all the participants, but also EC, I'd like to thank you again for the most interesting presentation. And with that, I would like to close this session. Next week, we will not have a Game Changer seminar on climate as our webinar next week on the 7th of July. We will have another Game Changer seminar a week later on the first James Webb Telescope images and data in the EC Game Changer seminar. And this time it will be on July the 12th. And with that, I thank everybody for attending. Again, thanks to you, Clement. And with that, I would like to close today's seminar. Thank you very much and have a nice afternoon.
Thank you very much. Bye, everyone.
Bye.